Next reaction is called hydration broadly. Hydration means adding H and OH across a double bond. Okay, how do we do that? Well, we have already come across one reaction. I'm going to take my favorite molecule, an unsymmetric alkene, and converting that into either that alcohol or that alcohol, and you can see this is a Markovnikov product. This is anti. Why so? Because Markovnikov said H always goes to the less substituted carbon. In this case, H went to more substituted carbon, right? So this is a Markovnikov product, this is an anti-Markovnikov product. So how do we accomplish this? Well, there are three different ways of doing hydration. First one is called acid catalyzed hydrolysis. What is hydrolysis? Hydrolysis means splitting water. Now, we think splitting water is H2O yielding H2 and O2. This is a electrolysis. This is a electrolysis. Electrolysis would be, this is how water is split into gases. Now, typical lysis of water is H plus and OH minus. This is a dissociation. So when we are talking about in organic chemistry, alcoholysis, for example, alcoholysis is ROH becoming RO minus and H plus. Aminolysis would be RNH2 yielding RNH plus plus H plus, NH minus, sorry. So this is aminolysis, is alcoholysis, this is hydrolysis, okay? It's just these are the terminologies that we can reserve for our later conversation. Acid, catalyzed, hydrolysis, there are three loaded words. Catalysis, what is the role of a catalyst? Catalyst speeds up the reaction. That's one role of a catalyst. Second role and more important role is it should not be consumed. It is used up but recreated. It is used during the reaction but recreated, and that is what the terminology we are going to use. Catalysis means an H plus is used up during the reaction and is released by the end of the reaction is finished. So this is the terminology that we are going to look at. Okay, anytime we see something used and then recreated, then it's called catalyst. Okay, so if we take a HA in water, depending on what acid are we talking, HA in water, depending on the strength, it can have an equilibrium of H3O plus plus A minus. Now we are not interested in A minus as anywhere here. We want the H plus coming from H2O. So how do you do this? We have done this before. In water, it's not staying as a HA, it is staying as a H3O plus. So when we, even if we write like this is not a realistic picture. So if you're looking for the mechanism, if you want to describe the mechanism, we have done this in hydrohalogenation. Now one problem of hydrohalogenation is it can have a competing product. We'll talk about that in a minute. So let's say I have H, OH2. This is where the electrophile is approached by a nucleophile, right? Giving you a transition state I like writing transition state in every reaction because it gives us a mental preparation of what is going down. This is like a storytelling, and the story is explicit. We are not skipping any steps. So the positive charge is now shared by these three atoms. This carbon, and this hydrogen, right? So these three are going to share the positive charge. But the pi electrons here are used as a collateral to do this process. Okay? So what's going to happen? This is where our regio selection comes in, right? If I continue, your regio selection, I'm going to write the one on the top to be thrown out. What is thrown out? This is the one that will be crossed out. Which one is crossed out? Connecting H here, placing a positive charge here, will be crossed out. That's selected to be thrown out. Which one is kept? Which one is kept for our further mechanism? Attaching H here and placing a positive charge here is our choice. This is a tertiary carbocation, this is primary carbocation. Our next step is bringing a nucleophile. By the way, we did use one H plus, so catalytic cycle has started, okay? But we didn't reproduce yet, so we didn't finish it yet. So who is going to be a nucleophile? In aqueous medium, water is the nucleophile. Now whether you come in synfacial or antifacial, it makes no difference because that H offers absolutely no resistance. That gives us a product which we don't really have to characterize in a stereo manner. So it's going to be like this, right? But now this oxygen has to be relieved of this charge. To relieve this charge, we have another water molecule is going to come and grab. What's the role? It's a base. What's the role here? It's a nucleophile. You know the role of water. In one case it's a base, another case it's a nucleophile. So when it does that, returns those electrons to this oxygen, we get alcohol. Now in the meantime, you might have noticed we finished the catalytic cycle as well. How did we finish the catalytic cycle? Well, we did release an H plus. We did give up one of the H pluses. Just the way we took in one H plus, we released one H plus. So catalytic cycle is completed. We also did right here, what did we do? We did the hydrolysis. We split water. We split H2O into H plus goes that way, OH stays here. So this is now acid catalyzed hydrolysis, right? And that's it. There is nothing more to it. Now, what acids are acceptable? Now, if you use HCl, HBr, and HI, there is a long shot, there is a possibility that we might get a minor amount, a tiny amount of Cl, a Br or a I might attack. Is that correct? Because that anion is still there. It's a competing in this case A minus. See, there is a minus here. You see there is A minus is a competing base or competing nucleophile. It should be here or A minus, right? Not here. So why did we pick water over this one? First of all, this is weak. Secondly, it is in lesser proportion. By the way, water is a solvent. That's why the proportion is not something that we can even compare them. Because for this is enormously large quantity. Okay? So that's why there is a chance that we might get a tiny bit of contamination if we use these. So we should avoid them. So who should we use? We should use something like phosphoric acid or sulfuric acid. And by the way, how much catalyst do you need? The amount of catalyst needed is tiny. So it's going to be trace. Trace amount is enough. So we don't need to add a large amount, we just need a drop or two of acid. And the reason these will not compete is because oxo anion OPO3H minus that was produced, or SO3H, these ions are lesser because of the bulk, they are less nucleophilic than Cl minus or Br minus, because Cl and Br don't have the entourage of oxygen or a size issue. Nucleophiles have to be really tiny for their effectiveness. So ClBrI have a possibility of functioning as a competing nucleophile, but these won't. So for this reason, we don't use HCl, HBr, HI for the purpose here. Okay. So this is acid catalyzed hydration. Now that's not a mainstream hydration. We have a typical name called Oxymercuration-demercuration. That's another method of doing it. Well, that shows something interesting. There is an element that we are projecting. What is that? Mercury involved. Hg2 plus salt are used. Acetate. Acetate is O C double bond O CH3 minus. Now for the sake of making it easier for us to communicate, I'm going to write OAC minus as my acetate. Okay. So mercury acetate is HgOAC twice. Okay, because it's a 2 plus ion. All right. So the overall reaction is this. Overall reaction is this. HgOAC twice, comma H2O. That's our nucleophile, that's our electrophile. Interestingly, mercury is our electrophile, water is our nucleophile. Now that's the mercuration part. Demercuration part is a whole new step. We use something called sodium borohydride. Sodium borohydride is what this is called, and this gives us the same product that we got in acid catalyzed method. And many a times we don't have to show that hydrogen, it's understood to be added, because in this skeletal drawings we normally do not show hydrogens on carbons, right? So we don't have to show. So this has a fairly elaborate mechanism, right? The mechanism is very interesting. So again, if you look at it, mercury is interacting with acetate, there's 2 plus ion. Now we can show this as a line. Sometimes mercury is known to make covalent bonds because it has a reasonably high electronegativity, so it can be considered it's going to make covalent bonds, but it's okay, we don't really have to lose our sleep over that. So since it is a Lewis acid, this is a Lewis acid. And what's the Lewis acid nature? What's the role of a Lewis acid? Lewis acid is electron acceptor. It's an electron acceptor, which is same thing as a electrophile. But do you think mercury wants to keep electrons? If it actually takes electron, it gets reduced, and it doesn't want to get reduced. So it's just a temporary electron holder. All right. Now, if we proceed with the mechanism, our transition state is going to be very similar to what we saw in previous cases. So it is going to make, right? So if it shares the positive charge with this, if it shares the positive charge, there will be only one positive charge left, and that means only one OAC. Let me keep both of them at this stage because let's not finish it yet. OAC, OAC, negative charge, and let's keep this as our transition state. Okay, let me erase this. Let's keep this as our transition state. All right. When actual donation of the electron has panned out, what would happen? Now we have a choice. Again, because two carbons are involved, this mercury has a choice of either marrying this carbon or this carbon. All right. So I'm going to write the one on the top, the one that need to be thrown out. And you know there is going to be selection made. The selection is this. When we attach mercury here, positive charge here, that's going to be the one that we are going to discard, the one that is choice. And there is a some kind of hidden voice that Marconico, right? Hg plus OAC minus. Why is it Hg plus? Carbon and mercury are known to make covalent bonds. So this is a very common knowledge. So we have a positive charge here created. Okay. Since it has covalent bond made, mercury now has only one charge. All right. Now, what do? We have a choice of water, because this is all in water. So there is a lot of water around here. So water can function as a nucleophile, do this or this, right? It should not really matter because the ultimate goal is adding H and OH, so we won't see the stereo effects anyway. So what is going to happen? If I continue it here, it looks like this at this point. What does it look like? We have Hg plus OAC minus. By the way, one of the OAC was kicked out, right? You remember that? It's still in the pot. It's somewhere in the reaction mixture. But now we have a OH2. Is that correct? Somebody has to come get this one of the hydrogens. Now the two candidates we have are that OAC and other one is OH2. And by pKa, we know this is going to be 10 to the 5 times, this is 10 to the 5 times more basic than water. How so? Well, this is where we can look at the pKa. H, O, CO, OH has a pKa around 5, while HO, H2 has a pK of 0. That means when we remove that hydrogen, create an anion, remove that hydrogen, create that nucleophile, that neutral molecule. I think I put a positive charge here, that's better, right? So we are comparing now the nucleophilic behavior or basic behavior. So you can say OAC is 10 to the 5 times stronger than H2O. So it's there. So it's not a big deal for us to bring this. And even if you write H2O, it's not really a really bad story because H2O is in large quantity. Frankly, in chemistry, large number of these are simply imagination, simply what we predict. So reality may be something else, right? So we have a OH there, and you saw there was a hydrolysis happened right there. You see there was a hydrolysis happened, water was split, but we still have this mercury hanging around. So we got to get rid of this. To get rid of this mercury, hydride, right? Now mechanism is not fully understood. Sodium borohydride is this, sodium ion and H, B, H, 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 and the positive charge, the negative charge is on hydride. Hydride. It's not a, it's borohydride. So this is our attacker. How does it do the job? we really don't know, and I think it's easy to conceive that this happens and this takes away those electrons. Now I really don't know whether that can be justified. Now if that actually happened, then you have OH and a H, and mercury must be neutral. Mercury must be neutral because it walked away with another electron. Then OAC is completely free to go anywhere. Okay? Now we don't worry about what happened, how it happened. The outcome is this. That's all that we worry about. And again, in this case, H did add, not in the step number 1. In our previous example, H did add as a first thing. H added first, then OH was added. In this case, OH was added first, then H was added. Even in this case, we got a Marconi coproduct. And you know, Marconi co means when H is added to the less substituted carbon, that can be branded as Marconi co. Remember, this example doesn't work only with this one. It can be used for any reactions. For example, does it work with this? Now this is symmetrical kene. Even though I'm taking unsymmetrical kene to display the importance of regio selection, even if I take a symmetrical kene, this reaction will give you product. Only thing is, this is called oxymercuration. Second step is called demercuration, which is using sodium borohydride. The product in this case will be pretty much same. There will be OH added here. Now since both of them are equivalent, there is another product that we will be saying that is going to happen as well. Now if this is the starting molecule, these two happen to be same products. However, what about this? If this is the starting molecule, now we can see these two are different molecules. This is different, this is different, this is different. So when you take a symmetrically substituted alkene, there is a possibility of a 50-50 mixture. Okay, and again, as a practical issue, we don't want to make multiple products. So sometimes if we are getting such multiple products, we avoid such roads because that product is of less value for our further use. But since we are simply learning how to do this, it shouldn't matter for us. Okay, so this is oxymercuration-demercuration. Next reaction is called hydroboration. This is also hydration. Remember, oxymercuration is also a hydration reaction. What does the hydration mean to us? As I defined first, I said adding H and OH across a double bond is called hydration, adding water. Okay, just like dehydration means removing water, this is adding water across a double bond. So we did add OH and OH across a double bond, and we followed the Marconi-Koff's guideline. So what about hydroboration? Hydroboration has boron involved. Boron is a unique beast. What is boron? Boron is 1s2, 2s2, 2p1. It has only 3 electrons in its valence. So this is one of the atoms that can violate and does violate octet rule. So if you take BH3, borane is an sp2 hybrid. It has an empty p orbital. This is an empty p orbital and it is a electron deficient. It is electron deficient. That makes it an ideal electrophile. It is also branded as Lewis acid. So all these characteristics makes this hydroboration an interesting diversion from our common game. So what is the overall reaction? Overall reaction is this. When you treat a molecule of alkene with borane. I'm going to write THF, and for now just remember this as a non-aqueous solvent. So we'll talk about what is that non-aqueous solvent mean to us. Okay, so BH3THF, this is a step number 1. Step number 2, we have to have a oxidative H2O2 in sodium hydroxide under basic condition. Interestingly, this reaction gives a H adds here, OH adds here, and it also, very interesting thing is they are both, see in previous cases we didn't worry about the stereochemistry. These are essentially syn to each other. That means H and OH are syn to each other. In previous 2 examples of hydration, we didn't really worry about H and OH, or we could not find out because there was a 50-50 chance because H was not offering any resistance. In this case, we have a syn facial addition. But it is an anti-Marconico. Why it is anti-Marconico? Well, in this case, H added to the more substituted carbon. This is exactly opposite of what this gave. This is H added to less substituted carbon. That's what Marconico was preaching, right? So how did we manage to do this? Remember, mechanism writing is a storytelling. All we know is this is added to this, and in the end this was found. So mechanism should be consistent. The story should be consistent with how did this happen. Alright, let's see the part of this mechanism that people have understood. The part of this mechanism that people have understood is this. And this, the first part, is not that difficult to predict. Remember, this is a solvent, so we don't have to pay any attention to it. It's just not water. So we have borane, and there is an empty p orbital that you can imagine, and it's begging for electrons. Boron is begging for electrons because it's only 6 electron system. It's electron deficient, a 6 electron system. And that means we have not completed octet. That means it's still looking for another pair of electrons. So it's a neutral. It's one of the classic example of a neutral electrophile. Boom, we got the electron. Now when the electron comes in, there is a wishful thinking and then there is a dangerous precedence. So let's see what happened. Transition state is again going to look like this, right? Boron, because always both carbons are participating in this game, because they are not going to say, well, you go along. Both of them are saying that these electrons belong to both of us. Okay, this is a system. Now, that doesn't mean that it made 5 bonds. It's interacting with it. That's why it's called transition state. There is no positive charge anywhere here, because this did not come with a positive charge. When this breaks loose, there are 2 possibilities, right? Regioselection. And at this point, you should be able to write them. So what do we write? One of them is connecting boron to this carbon and placing a positive charge on this one. Second one would be adding or attaching boron to this carbon and that makes positive charge on this one. There's something missing here. Can anyone spot something missing here? We took a not neutral molecule and neutral molecule. Is that correct? This is neutral, this is neutral. And if we say this is positive suddenly positive, something is missing. Neutral should give you neutral. There is no reason for charge to be developed. Somebody has a negative charge. If this carbon has a positive charge, somebody has a negative charge. Who has a negative charge? Boron has a negative charge. Boron got the negative charge. Why negative charge? Boron gained an electron. it gained one electron here. Why one? Why not two? Well, it gained one because if there are two electrons here, one still belongs to this carbon, only one of them is a share of boron. So the boron has gained an electron. Now here comes the electronegativity quabble. Who is more electronegative? Who is more electronegative? Carbon is more electronegative. We know that, right? Compared to boron. If carbon is, I would say 2.5, this is like 2.1 or I think it's 2.1 electronegativity. So there is a significantly lowered electronegativity. And if that is the case, how can boron have a negative charge and carbon have a positive charge? That's violation of formal charge rule. So suddenly boron realizes the problem and it makes a peace offering, saying that, okay, take these electrons with hydrogen to you. This is called hydride transfer, hydride slide, because it went from boron to this carbon, because this is the carbon that is troubled. It immediately gives it so that it doesn't have any guilt anymore. So now, if you look at it, if boron is this way, that H must also be on same side, right? It has to be from same face. And this is where I'm talking about a facial, synfacial. And we can see there is a synfacial attack happened already. So we have a H here. Right here we violated the Markovnikov rule. You see that? Markovnikov did not like H being added to the more substituted carbon. But because of the necessity, this boron has to do this. What is the charge now? The molecule is neutral, right? The molecule is neutral. Now what happens is, this is step number 2. So we finished the step number 1. So we reached this. This is neutral molecule now. There is no charge because the positive charge, negative charge was there. By moving those electrons there, that carbon became neutral. But by losing those electrons that went with the hydrogen, boron has no charge. So molecule is happy. Okay? But this is not the end of it. You see, we created a narrative that is anti-Markovnikov already. Now, what happens next is controversial. Controversial, some people try to say that the OH minus is the one that attacks here and replaces that. Some people say that's a H2O2, the OH in H2O2 is what? I prefer to write it like this. I prefer to write like this. I would say there are 2 electrons here, there are 2 electrons here. The transition state is going to be like this. This is my, after looking at several documents, I have seen that this is more consistent because while the base is necessary, there is a one reason why you will have OH coming from same side as a H. It can be justified because this H2O2 has to come from same side as the H. So there are 2 reasons. One, presence of H2O2 otherwise not justified. Second, it is going to be syn product. From that idea, I am proposing, or I am saying that final answer is this. You have a H here and OH here, one of them. So it's going to be on same side, and the product will have boron with H, and of course OH, right? Now, do we really care for this one? We don't really care. Now we know that if we use H2O2 and boron in this reaction, the final answer is called boric acid. That's another reason why I think that H2O2 is directly involved in splitting process. This OH is just there as some kind of a mediator. Now, in some books they tend to write OH is the one that attacks here and kicks out a boron. I just don't see if that is the case, I don't see a purpose for H2O2. And I don't know how you are going to make that. This is called boric acid. Boric acid is a common product in this reaction. Well, while we are paying attention to this, we are losing attention from this one. I don't want you to lose focus from this one. This is our ultimate goal. And what happened is H and OH are syn attack. They are syn products, and they have a H and OH are same side, and OH has gone to a less substituted carbon, H has gone to more substituted carbon. Now, we can only make that anti-Markovnikov statement if and only if we have unsymmetrical kin. Now, when you have symmetrical kin like this, let's say, I'm putting that methyl for a reason, and you'll see why. And if I didn't, you wouldn't see what I was going to see. All right. So if I say BH3 THF, step 2 H2O2 NaOH. By the way, this is non-aqueous, this is aqueous. NaOH is not going to exist in a non-aqueous. It's not going to become OH minus for any reason. Now, what is the purpose of OH minus? I have a hard time explaining, so I'm not going to begin that. Even this one, I have a hard time explaining it. Okay? There is nobody has yet figured out how does this happen. We can simply say magically this is transformed into this one. Okay? And even if you thought that way, it's not a big deal. Nobody's going to analyze this any detail. Okay? Just being aware that's the product is the issue. Now, what happens in this case? In this case, since there is no regio selection, we should be getting two products. We should be getting a OH here, H here, and H here, OH here, and 50-50. There is no reason why one of them is more favorable than the other one. And by having that methyl group, these two became different. If I didn't have the methyl group, these two would be identical molecules. So just wanted to show you that there is no regio selection. No regio selection if symmetrically substituted alkene is used. Okay. Now, I don't have to give sufficient examples of this, but I'll give one example just to show you that what is the consequence of carbocation formation. Now, if you look at a reaction where, let me see, I'm going to take this example. Okay, I will take this example. Actually, I don't know why I drew this. Don't really need that. Okay, so I'll just leave it that. Let's see what is the product if I use HA, H2O, if we use HgOAc twice H2O followed by NaBH4. And the third one is BH3THF, BH3THF followed by H2O2 NaOH. What are the products? Now, interesting thing is there is a finite lifetime for a carbocation here. The product in this case is going to be, and product in this case is going to be this one. Product in this case is going to be this one. Why did I do that? Product in this case is going to be that one. Okay? And you know why? I'll come to that. Product in this case, however, is going to be because we didn't see any finite lifetime for a carbocation, and even if there is a carbocation, it wouldn't have made a difference. OH is going to be here. See, you might be tempted to write the product of this one is going to be this. See, that is our H adds here, OH adds here was our expectation. But in these two cases, there is a finite life of a carbocation. So what happens is, when there is a carbocation formed, you have to consider hydride shift. That hydride shift makes this carbocation, right? And that's why you get this product. In this case, we don't have to worry about that. We don't have that. So this is something that you have to be watchful when you are dealing with questions on a test. All right? This story ends here.